Hi there, welcome. It's Chem Coach Powers, and today we're going to be talking about limiting reactants and percentage yields. So let's get right to it. This is going to be great stuff. So far, we have been talking about examples that are getting closer and closer to what we'd use in a real life example as far as in the laboratory. And today we're going to add one more little piece to that, what a limiting reactant is. Because, you know, when you're in the laboratory, you've got chemicals, storage shelves full of chemicals. And if we want you to do a reaction, then those two chemicals have got to react to each other. So far, we've kind of just been pretending that one chemical is the only one that really matters as far as the amount is concerned. Now we're going to be like, you know, in real life, we actually have both chemicals and the amount of that is actually going to be significant. So let's get to it. So our objectives here today: identify the limiting reactant and excess reactants for a reaction, use the quantity of limiting reactant to calculate the theoretical yield, and then perform calculations involving percentage yield. So our criteria for success: given amounts of two reactants in a chemical reaction, I can determine which is the limiting and which is an excess. And then I can use the limiting reactant to calculate then the theoretical yield for the reaction. And if I have the actual yield and the theoretical yield for the reaction, whether I determined it or whether it was given to me, then I can calculate the percentage yield for the reaction. All right, so what is a limiting reactant? Well, it's kind of fun to use a little example of a hamburger or a bicycle, a few different examples that we can use to talk about limiting reactants. But basically, the limiting reactant is a reactant that limits the amount of the other reactants that are going to be able to combine. How much of the total substance you are going to produce is based upon the one that is present in the least amount. Now, when I say least amount, though, you have to be very careful to realize, you know, I'm not talking about the number of grams, for instance. The limiting reactant is going to be completely used up. Okay, so whichever one gets completely used up and then there's going to be some left over, the one that's left over is called the excess, and the one that gets completely used up is called the limiting reactant. Okay, so we have the limiting reactant and the excess reactant. The excess is not going to be completely used up. Some of it's going to be left over, and the limiting reactant is going to determine how much of the final product I can make. So let's look at an example of a hamburger here. All right, in this example, you can see that we've got 3 hamburger patties. We've got 6 sets of buns, and we've got a dozen pieces of cheese, right? Well, let's say that we want cheese on the top and the bottom of our bun. We want some good cheeseburgers here. And so that means that I'm going to be able to put 2 slices of cheese, one on the top and one on the bottom of each of those 3 patties. And so I'm going to use up 6 of my cheese slices. I'm going to use up 3 patties. And then I'm going to have some leftover buns as well as my leftover cheese slices, because there's only 3 buns that need to be used. And so that means 3 buns will be left over along with 6 cheese slices. Okay, so the limiting reactant, the thing that limits how many cheeseburgers you can make, is the hamburger patty. The other stuff, that's the excess. That's the stuff that's left over. So that's basically all limiting reactant is. Now, we're going to take that concept, which is a simple concept, right? We're going to take it and now we're going to just apply it with some numbers to see if the numbers can tell us which one's left over. And that's the part that sometimes can get a little bit confusing. All right, so if there are 2 or more given amounts in a problem, we know that it's going to be a limiting reactant problem. So as soon as you see 15 grams of this and 3 grams of that, and then they're both reactants, then you got to be like, okay, this is a limiting reactant problem. And I've got to figure out which one is limiting before I can do the rest of the problem. Because if you start solving the problem with one of those and it's not the limiting and it's the excess, then your answers are going to be totally wrong. And so you've got to figure out first which one's the limiting if they give you 2 amounts for both of the limitings. For both of the reactants. Sorry. All right, so your steps to finding the limiting reactant. 1, first you're going to write and balance your equation. These are stoichiometry problems, so make sure you have a balanced chemical equation. Figure out what your knowns and unknowns are, right? And then, of course, we're going to use our normal dimensional analysis. We're going to just go through and do our conversions, right? So unit analysis, cancel out the stuff that needs to be canceled out. Nothing crazy there. But here's the deal. You need to convert your grams to moles. Now, there's a couple ways to do limiting reactant problems, and I am not really set on you doing it one particular way. Okay, so if you want to do it another way, that's okay. But you have to make some sort of a obvious piece of work in your work that shows why one of them is the limiting. Okay. And so in this case, step number 3 is telling you convert all of your grams of your reactants to moles. So get them both set in moles. Now it's important that you have moles as your value, okay? Because limiting reactants are based upon the molar amounts, not upon the gram amounts, but upon the molar amount. So you've got to convert to moles one way or the other, okay? So at least convert 1 to moles, and probably if you're taking this method, you're going to convert both to moles, okay? All right. And then you'll notice here we have a little shortcut. It says determine which reactant is limiting. It says shortcut, divide the number of moles of each reactant species by its coefficient. So let's say you had 2H2O, and then you had, 1 mole of H2O. So you would divide that 1 mole of H2O by its coefficient, which in this case would have been a 2. And if you do this, it's a little shortcut, then the smallest number is going to be the limiting reactant. Okay, this is a good way to do it. It's not the only way to do it. It makes sense to some people, doesn't make sense to other people. You need to figure out which way makes sense to you as you figure out how to solve these problems. All right, so then you start with the number of moles of the limiting reactant. You don't have to go all the way back to grams again. You've already come from grams to moles. So now just start the rest of your problem in moles. You're good to go. Now, some of you are like, what? I don't get it. What are you talking about? Well, let me take you through an example. You're going to get it. It's going to make sense. You're okay. Just hang tight with me, all right? Here we're going back to the rocket fuel, right? Hydrazine. We did this in another problem earlier on with one of our bellworks or catalysts, right? And so we've got this hydrazine, and it says some rocket engines use a mixture of hydrazine and hydrogen peroxide as a propellant. And this is the reaction. Hydrazine plus hydrogen peroxide, 2 hydrogen peroxides, gives you nitrogen plus 4 H2O. All right, so we've started with a balanced chemical reaction. We know it's balanced because they've thrown some coefficients there for us already. So sweet, don't have to balance it. Nice. But now they give you those 2 parts, right? Remember I said you've got to look out, and if they give you 2 parts, that's what you really want to look out for. Well, oops, I'm going to go back to red here on this one. I think red will show up better. Look, I've got 750 grams here, and that's of the hydrazine, right? And here's my second part. So that's hydrazine. And here's my second part. I've got 500 grams of the hydrogen peroxide. Ooh, those are both reactants, right? And remember, I said if they give you amounts of both reactants that you know it's a limiting reactant problem. That's the key right there. If I only gave you one, if I said 750 grams of hydrazine and I didn't tell you how many grams of hydrogen peroxide, then you wouldn't have to worry about this. You just go with the 750. But if we give you 2 givens in this type of problem, you got to be like, oh, I got to figure out limiting reactants first. Now, the final goal here is to find out how many grams of water are formed. So in order to figure out how many grams of water are formed, I've got to figure out which one of these is limiting. Now, again, I said there's a couple ways to solve these problems. One of them would be you could actually go through, start with 750 grams of hydrogen and start with 500 grams of hydrogen peroxide, take them both all the way to water and see which one is the least, and that's your answer. Okay, that one really makes a lot of sense to a lot of students. It makes sense to me, but it's also a little bit more work. So you don't have to do that. If you wanted to go through the whole thing, you can. But there's an easier way. You just have to kind of wrap your mind around it, all right? So step 1, yes, it's balanced. Sweet. Step 2, we know our unknowns, and we've got 2 reactants, so we know it's a limiting reactant problem. So now step 3 says, let's convert these to moles, okay? So this should be a little over to the side here. It should be right over there. So I convert my hydrazine to moles first, and I get 23.4 moles. And then I convert my hydrogen peroxide, that should be over there a little bit further, to moles as well. Now notice that we've got now 23.4 and 14.7. Now remember, it said the shortcut is to divide each of the moles by the coefficient. So if we go back to that balanced chemical reaction, go back to that one real quick. You notice we have a 4 in front of the water, and a 2 in front of the H2O2, and a 1 in front of the N2H4, right? And so I just have 1 in front of my hydrazine. So all I have to do is divide that one by a 1, okay, because that was the coefficient that was in front of my hydrazine. And then I take my hydrogen peroxide and I divide that one by a 2, because that was the coefficient in front of the hydrogen peroxide. Now I've got some new numbers, right? 23.4 and 7.35. And remember, it says whichever one is the lowest, then that's your limiting, okay? And so the H2O2 is smaller, so that's the limiting reactant. Now, the reason that a lot of times I don't like to use this method is because these numbers don't really mean anything. They just are helping you to figure out which one is a limiting reactant. But they don't really tell you anything in particular as far as where you go from there. Where you have to go now is you have to go back to that point where you had moles. So now I know that the H2O2 is the limiting. I've got to use this 14.7 moles of H2O2. That's the part I have to go to. And now I start my next problem with that. Now, again, that's why sometimes I don't like to use this method, because it confuses students and they try to use these numbers. They try to use the 7.35 or the 23. No, don't do it, okay? You got to go back to the number of moles. Those numbers don't really mean anything. It's just helping you figure out which one's limiting. Okay, so now I go back to the moles. And again, I apologize. These things are a little bit offset. And so I use my mole ratio. Where am I trying to go? Remember, I've done these now. I've done a lot of stoichiometry problems now. I'm going to water. And so I've got to go to moles of water first with my balanced chemical equation coefficients. And then I've got to go to my periodic table, get my gram molar mass. And then I'm going to get my answer. My answer in this case is 530 grams of H2O. Why 530 point? Remember, we had 3 sig figs in our original work, right? We were starting with our original work of 500. That was 3 sig figs. So our final answer needs to be in 3 sig figs as well. Okay, so now you've done one. That was a limiting reactant problem. Like I said, if you go and you look up a couple other ways to do these on YouTube, you'll probably find a couple slightly different variations of this, including the one I talked about as far as going all the way through. The one that I actually personally use is not even one of these. There are a few ways to do it, but as long as you show your work, I'm okay with it, okay? So let's see if you can do it, all right? So here's your problem. You've got 20.5 grams of chlorine and 20.5 grams of sodium reacting to make sodium chloride. Which is reactant is limiting, and how much sodium chloride is produced. So you've got to start by writing your balanced chemical equation and then going for it, right? All right, so we're going to pause, and you're going to see how you do. Ready? Here we go. And you're back. Thank you for coming back. I'm so glad you're here. Balanced chemical equation. So we start with that balanced chemical equation. Did you forget that chlorine was Brinkelhoff? By golly, I bet you about 10 of you forgot. Chlorine, remember, is a Brinkelhoff element, which means it's diatomic. You've got to have Cl2 to start. And if you didn't do that, then everything else is wrong. Right? I mean, it drives you crazy sometimes. One little thing can screw up the rest. That's all right. So now it's balanced. You can see what that looks like. I've got to convert grams to moles for both of these. So I've got my 20.5 of chlorine and my 20.5 of sodium. Now, notice how we used in this particular example, we used the exact same amount of both of these. Why did we do that? So that you can figure out, oh my goodness, these things are not dependent upon mass. Remember, it's dependent upon moles, not mass. We gave you the same mass so you could see it doesn't matter what the mass is. What matters is the moles. So I convert those to moles. Now, how did I do that? Remember, you go to the periodic table and you grab the molar masses from the periodic table to get those molar masses. That's what you should have gotten. And then if you want to go to the next step, you have to divide by the coefficients, right? That little shortcut. So you divide both of those by the coefficients. So the chlorine by 1 and the sodium by 2. And then you've got these two numbers. Now, which of those two numbers is the smallest? Okay, you can figure that out. 0.289 is the smallest, right? That means that chlorine is your limiting reactant. Now, a lot of times we're just going to say, what is a limiting reactant? And you can just say LR. LR stands for limiting reactant, okay? So that's your limiting reactant. Are you going to use this number? No. Are you going to use this? No. Those are not meaning anything, right? Those are just kind of telling you which one's limiting. They do not use those numbers. You got to go back to the moles, all right? Hopefully you did that. So go back to the number of moles, 0.289 moles of chlorine. And then as you take that and convert to moles of sodium chloride, we didn't have to go to grams all the way this time. So now we have 0.578 moles of sodium chloride. Did you get it? I hope so. I bet you some of you did. Yep. If you go to grams, oh, did they ask us to go to grams? Maybe I need to go look at that question again. If you go all the way to grams, sorry, this is in 2 steps. Normally we keep those in 1 step. I guess they asked you to go to grams. Sorry, I didn't pay attention enough. 33.8 grams of sodium chloride. There you go. Okay, now can we do whoop whoop? You're like, powers, I thought I had it wrong, but I had it right. Ugh. Stop beating your screen. It's okay. It's just my fault. All right, let's do another one. Okay, we're limiting reactant problem number 2. Carbon reacts with steam at high temperatures to form hydrogen gas and carbon monoxide gas. If I have 2.4 grams of carbon exposed to 3.10 grams of steam, identify the limiting reactant. So steam is tricky here because this will throw people sometimes, but you know what steam is made out of, right? It is a chemical formula. Okay, we use the word steam, but we know that we're talking about agua. Okay, so let's see what we get. What mass of each product is formed? Well, we know what we got to start with, right? We got to start with the balanced chemical reaction. Did I almost tell you the answer? Sorry, that was close. All right, so pause it, and we'll practice it. And there's the pause. Beep, beep, and we're back. All right, so what mass of each product is formed? Started with our balanced chemical reaction, right? And so we've got to say, all right, carbon, C, plus H2O gives you H2 plus CO. Oh, that's pretty easy. It's not too hard to balance. It's already balanced once I write it out correctly. Did you remember Brinkelhoff? Hydrogen is part of Brinkelhoff. All right, so then you can see... And this portion, where's my pen? There you are. If you can see in this portion that we got to the moles, right? And then we had to divide by the coefficients. In this case, both of them were 1 for the coefficient. So the one that was the smallest was just the same 0.172. Now we can actually use that same number because it isn't any different than the number of moles, right? So we can say, all right, 0.172 moles. And, you know, as you're going through and doing this problem, you'll notice that in this question, they wanted the mass of each of the products. And so you had 2 products, so you had to come up with 2 answers. My goodness, so hard, right? Well, anyway, you've got the masses of both 0.347 and 4.82 as the masses of those. So 0.347 grams of hydrogen and 4.82 grams of carbon monoxide. All right, so you're getting pretty good at this, right? It's not too hard, not too hard, not too hard. All right, so now let's go on to the next one. Now, this one is even easier. The harder one was definitely the limiting reactants. And if you're still having trouble wrapping your mind around it, read through the book, talk to me in 7th hour, talk to me in class, and let's see if we can figure it out. Give you a couple of examples. Got a lot more different kinds of examples that we can talk about. So percent yield basically is saying what percentage of the amount of product that we expected did we actually get. Okay, so we expected to get this much, and we didn't get that much. We got this much. So what percentage did we actually get? That's what percent yield is all about. So you're going to look at 2 terms that we have to be familiar with here. One of them is the theoretical yield, and the other is the actual yield. So the theoretical yield is how much we should have gotten if we were to have, you know, done, like when we do the math tells us this is what we should be getting. But we don't always get that in the lab. And so the actual yield is what you would have actually gotten in the lab, or maybe it's an example in the, you know, in the problem, and they're like, it was actually this, or it will say, you know, actually acquired, or it might not use even the word actual. It could just say the yield for this experiment was blah. Well, you know, that's the actual yield, okay? The measured amount that you got from the reaction, okay? Now, remember, we will always give you the actual yield in a percent yield problem, okay? You can't do the problem without it. Either you do the experiment or we give you the actual yield as a value. And so, yeah, it's going to be easy, right? It's just doing a little division problem and then multiplying by 100. All right, so percent yield is the efficiency of your reaction. So we take the actual yield divided by the theoretical yield, multiplied by 100, A over T times 100, and we get it. So it's pretty easy, right? Just make sure that as you're going through the problems, here's the thing. Sometimes we're going to give you a percent yield problem and we're going to give you the actual yield. Sometimes we're going to give you a percent yield problem and we're going to ask you to go through all of the holy moly, all of that stuff, the stoichiometry, the limiting reactants, everything. We're going to ask you to go through all of that stuff. So you just have to say, all right, well, sometimes they're going to be more work than other times. But the percent yield part is always the same. It's just actual divided by theoretical times 100. And that part is easy, but sometimes you have to go through all the steps before that to even figure out what your theoretical yield is. Okay, so step 3 here, you can see, calculate the theoretical yield as necessary. Most of the time, we're not going to make you do percent yield problem and do the whole theoretical yield first. It'll be a theoretical yield problem and or a percent yield problem, and we're going to give you the actual yield. But know that could happen. Okay. All right. So, boom, boom, done. Let's see it. Let's see an example. When copper metal is placed in a solution of silver nitrate, silver metal, and copper 2 nitrate form. If the theoretical yield is 17.0 grams of silver, but only 15.2 grams are actually, what? Actually? Actually, all right. So here's that key word, right? And again, we might not always give you the actually word, but man, if we actually do, it's actually really cool. All right, so it's easy. 15.2 grams are actually produced. What's the percent yield? All right, so do I need an equation? Do I need to go through the whole figure out the theoretical yield stuff? No. They gave me the theoretical yield, right? Yay, thank you, people. Thank you for giving me theoretical yield. All right, so that part is done. So we don't have to do the whole equation stuff. All we have to do is do our little formula, and man, this is so easy. 15.2. You know, we could be good. We could be good and show our units here. 15.2 grams, 17.0 grams. Have those divided by each other, multiply by 100, and your final answer is 89.4%. Now, when you do percentage problems, remember, I'm not worried about your sig figs. But I would like to see you give me percentage problems to the tenths or to the hundredths place, preferably to the hundredths. Tenths is going to be fine, but don't give me just 89%, right? Like, give me at least to the tenths. All right, so that's how easy that is. Woo! Should I box that answer? Yeah, I should probably box that answer. Got to box all my answers, Power, don't you know? Won't get my points if I don't. All right, so your turn. Yay. Now notice here that this is one where the theoretical yield is given, okay? So I'm going to do one here in a minute where it's not given, but it's okay. So this one, it's given. You've got this. Here we go. When octane is burned in oxygen, carbon dioxide, and water are produced, the theoretical yield for this reaction is 454 grams of water, but only 392 grams are actually produced. Again, we won't always say that, but when we do, it's actually cool. What is the percent yield of the reaction? All right, pause and practice this, see what you get, and boop, and you're back. Thank you. All right, so let's see what you did. Oh, you got 86.3%. How do I know? Because you're smart, and yeah. What did you do to get the work, for the work to get there? Well, what you did is you took the actual divided by the theoretical, multiplied it by 100. Right? Yeah. Pew, 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 pew. That's what you did. And did you box the answer? Of course you did, because you're better than the PowerPoint. All right, 86.3%. All right. Uh-oh, no theoretical yield given. Oh, that's okay. We can figure it out. It's just doing what we just did earlier, right? All right, so methanol can be produced by the reaction of carbon monoxide and hydrogen gas in the presence of a catalyst. And so here's your formula. Yay, I don't have to figure out the formula. It's done. All right, so the formula is done. If 75.0 grams of carbon monoxide react with excess hydrogen, produce 68.4 grams of methanol. That's what that's called. Methanol is right here, and that methanol is meow. Okay, so 68.4 grams of methanol. What is the percent yield of the methanol? All right, is the equation balanced? Yeah, how do I know? Because if I've thrown a coefficient in there for you, I balanced it for you. I'm not trying to trick you. All right, so now what's given? The mass of carbon monoxide, and I'm going to use that to find the theoretical yield, and then the actual yield of methanol. Now, unknown percent yield of methanol. That's what I got to find. Okay, no problem. I can do that. So can I figure out the mass of carbon monoxide? Now, notice that there's a very key phrase here. First time we're having to really focus in on that phrase. Excess hydrogen. Oh my goodness, thank you. That means this is not a limiting reactant problem as well, right? Man, you don't have to give me more than I need. So yeah, this is not a limiting reactant problem. This is just a regular stoichiometry problem. Got to go from 75 grams of carbon monoxide, and I got to go to my grams of methanol. So again, it says that it reacts to produce this much. How much is it actually supposed to produce, right? What does the math say it should be producing? This is what the lab, okay, it reacts with this to produce this. It actually did this. This, even though I told you this, not always going to say actual, but this actually produced 68.4 grams. But what did the math say it should have produced? Okay, so that's where you come to the theoretical yield. So carbon monoxide is limiting. It told us the hydrogen was in excess. We don't have to do a limiting reactant problem. So we just got to convert 75.0 grams of carbon monoxide to the grams of methanol. Basic stoichiometry problem. Boom, 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 boom. Done, right? You see what you did there? You went from grams of carbon monoxide to moles of carbon monoxide, right? And then we went from moles of carbon monoxide, cancel those out. And now we're in moles. Where did I get those numbers from? Boop, 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 boop. I got them from here and here, right? Balanced chemical equation. And then I go to the periodic table, and I got that number from the periodic table. So my answer in theoretical yield, 85.9. I was supposed to get, according to the math, I was supposed to get 85.9 grams of, oh my goodness, where are my units? Ah, I tell you, peeps. All right, CH3OH. I was supposed to get that many grams of that. I didn't get that many grams of that, right? I only got 68.4. That's my actual yields. This is my theoretical yield. Okay, so now let's do actual divided by theoretical times 100. Oh, this not so hard, Powers. Thank you. I know how to do it now. See? Okay. Can you do it? Are you going to do it on your own? Yeah. You got this. You got this. All right, your turn. Again, the theoretical yield given. Quicklime, calcium oxide, and carbon dioxide are produced by roasting limestone, calcium carbonate. When 2,000 grams of calcium carbonate are heated, the actual yield of quicklime is 1,050 grams. Now, do not get confused. This is not your theoretical yield, right? This is, it tells us the actual yield, right? 1,050 grams. But theoretical yield has got to come from this known. This is calcium carbonate. And I'm not looking for calcium carbonate, right? Quicklime is calcium oxide. So I've got to go to calcium oxide from calcium carbonate. What's the percent yield? All right, you can do this. We're going to pause, and you're going to come back, and you're going to show me how victorious you are. Ready? So pause it, and you're back, and you did amazing. I know it. Your formula. All right, I hope you got the formula. I hope you got the formula. You figured out carbon dioxide, right? Again, remember, everything starts with a formula. So if you don't get that formula right, oh, yeah, what's it going to be? You got to figure out how to do these formulas. If you don't know how to figure out these formulas, you and I need to talk, because we got to figure this stuff out. So once we've got that formula, then we've got to figure out the theoretical yield. So we've got to start with our, yeah, were we in excess? Yeah, remember, this is only one reactant. So there's no way to do a limiting reactant problem any other way than just using the one reactant, right? So there's only one reactant, no limiting. And so now we go through and we do our steps. 2,000 grams. Oh my goodness. There's no work. It just drives me crazy. All right. We've got to start with a calcium carbonate, right? So that's calcium carbonate. And then this is calcium carbonate. We go to the periodic table. That's calcium carbonate. This on the bottom is calcium carbonate to cancel out calcium carbonate. But this is calcium oxide, our quicklime. And then this is calcium oxide to cancel out. So we end up with calcium oxide. Who doesn't show their work like that? All right. So then we get 1,121 grams of calcium oxide. Now that, my friends, is not the same as the actual yield. Here was our actual yield, right? And so now we've got to figure out our theoretical yield. This is what you did. And you came up with 93.67% as our percent yield. Boom. Shakalaka. Got it? All right. All right. So now we've done it. We've done all these different types of things. Let's see how good we are. We are so good. Let's look at our review. What did we learn today? We identified the limiting reactant and the XX reactants for a reaction. Which one's going to get used up? The limiting. Which one's going to be left over? The excess. We use the quantity of limiting reactant to calculate theoretical yield. Just did that. We performed calculations involving percentage yield. All right. So we had to do, for this last problem, we had to calculate the theoretical yield and perform calculations involving percentage yield. So we had to do the bottom two. We didn't have to do the top one for that last problem, but we did that earlier on. All right, and so our criteria for success. Given amounts of two reactants in a chemical reaction, I can determine which is limiting, which is excess. Ooh, yeah, I'm so good. I'm a great chemistry student now. I can use the limiting reactant to calculate the theoretical yield for a reaction. And given the actual yield for reaction and the theoretical yield, or means to determine it, I can calculate the percentage yield for a reaction. All right. So thank you guys for hanging with me today. This stuff is, again, what we're doing is it's more and more applicable, right? Like we're getting into what you actually use in the lab more and more as we go through the year. And so now I've got two chemicals on the shelf and I got, whoa, I need to have this much. How much, Teach? You said you want that much of my products? Okay, well, now I've got my two reactants. Which one's going to be my limiting? Now, in the manufacturing process, the reason this is so important is because when you're in the manufacturing process, I want to use the cheaper chemical to be my excess. And I want to use my more expensive chemical to be my limiting. Because if there's going to be waste, let's make it the cheaper chemical, right? So expensive chemical becomes limiting, and then the cheaper chemical becomes the excess. That's the way to do it, and that's how you run it in real life. All right. See you guys. Have a great day. God bless you, and don't forget to be kind to each other, because if you're not kind, that's mean. Bye.